Welcome to this new series of collective talks. Today we are going to be talking about Kubernetes and what are containers before starting on Kubernetes and orchestration and a lot of other good stuff. I'm Praveen Salitra, leading engineering here at Enoch. Been here almost for 6 years, and we are based out of Naperville, Illinois, here in Chicago. So who is Enoch? We are an engineering organization with very high degree of technical expertise in data visualizations and applications. Applications can be your web applications or mobile applications, in some cases desktop applications as well. For the last 3 to 4 years, pretty good experience that we have had in streaming data engineering. And then of course, for the last couple of years, have made a lot of significant progress into cloud native DevOps as well. So just to summarize some of the work that we have done here at Enoch, we mostly are working with data intensive applications. We touch some of the pretty cool data engineering frameworks like Kafka, entire ecosystem of Kafka from Confluent, Spark, Elasticsearch, various or multi-tenant APIs, and a lot of client apps, client-side apps, whether those are web, mobile, or desktop, as I said before. So one of the things that we have learned for the last 4 years or so is some of the keywords like scalability, high availability, continuous deployments, monitoring, alerting. Those are just not just the keywords for our engineering teams, but those are deeply ingrained in the way we code, we test, build, and deploy. So for example, all of our UI and REST APIs are containerized. They run on Kubernetes these days, even to the extent our Jenkins is actually running on Kubernetes. Our WordPress sites for us, as well as our clients, is running on Kubernetes. Kafka is running on Kubernetes. Even our VPN server is running on Kubernetes. And a lot of apps, including databases as well, are running on Kubernetes. So to an extent, we have mastered or coined the term called Dockerize everything. Let's talk about the Cloud Native series. The plan right now is we will have this particular session every Thursday, at least for the next 2 months, 7:30 p.m. Central. And then today we're going to be talking about just containers in general, what those are, why do you need orchestration for the containers, and then of course, why Kubernetes is the gold standard in the container orchestration. So we'll go through an architectural overview of Kubernetes. Next week, we'll be talking about how to set up Kubernetes, whether it's your local machine or on a cloud provider like AWS. Following to that, we will understand how Kubernetes can be secured using its internal RBAC. And then, of course, how can we bring it together with AWS IAM? And then following few sessions are going to be around how do we create Kubernetes objects for stateless workloads, for stateful workloads, how do you do proper load balancing with ingress controller and save money on that, how do you set up SSL configuration, and then, of course, towards the end, how do you do disaster recovery, how do you monitor using Prometheus, your entire cluster, including your apps and nodes and containers and pods and everything. I have last sessions marked as reserved right now. Depending on how the other session goes, we'll figure out a cool topic for the last session as well. So one more thing, except the session today. Today's session is going to be more theoretical. I only have slides, but all the other sessions, remaining sessions, they're going to be more on hands-on workshop format where I will be showcasing some of the things live by coding and doing all these cases. So just for today, it's going to be just the slides. I think those will still be fine. So some of the questions that we'll try to answer today are like this. So what is a container? Why you should use container? What infrastructure do you need to run containers? How Kubernetes fits into this world of containers. What are the components that make a Kubernetes cluster? Because that's very important to understand what is the architecture behind it. Then, of course, the big question, how Kubernetes orchestrate this containers ecosystem that you have. And then, of course, who are other options, competitors for Kubernetes. One more thing, if you have any question, you can keep on typing here. And then towards the end, I will try to answer those questions as well as much as I can. If time runs out, I will post questions and answers on the blog. And this session is getting recorded, so you will have the recordings available. Cool. So let's start with a container, right? You may have heard about Docker. So out of all the container runtimes which are available, Docker is the most popular. Came somewhere in 2013. And there are other options as well for containers. One of the other lesser known names are Rocket, It's spelled as RKT. Then also there is something called open container from OCI specification. So how Docker defines a container? The definition here is kind of related to image, which we'll see what's the difference between an image and a container within a couple of slides, but the meaning still stays the same. So it's a lightweight, standalone, executable package of software that includes everything needed to run an application, whether it's code, whether it's runtime, whether it's system tools, libraries, settings, everything. So the question is, okay, didn't we already solve this problem almost 10 years ago when VMs were popular or starting to become popular by AWS, right? In turn, Netflix is actually built on this VM-centric approach where they started deploying one app per virtual machine. So let's go back and understand what was the configuration at that point. So you had an infrastructure provider, in our case, maybe AWS or Azure, or can be Google Cloud as well. And then you had a hypervisor managed by the cloud provider, and then you would go and configure a VM, install your operating system, maybe Ubuntu or Windows, and then you will configure your app or deploy your application there. If you go with this logic of one app per virtual machine, you can create an entire orchestration just around that. Netflix did it way back in 2013 at that point. So what's the difference with containers in this picture? So with containers, you actually remove the necessity of having a guest operating system, which is very heavyweight component, which can be very heavyweight component in your virtual machines. So instead of that, what you use actually is the runtime from Docker. So think of it like JVM, right? That provides portability for your Java applications across different systems or platforms. Same thing, you can create an analogy for Docker. And then your applications can be very small piece of executable packages. They will have their own code plus also the libraries required to run them. So think of, let's say maybe app A is actually a Java application, app B maybe a Node.js application, app C can be a PHP application, and whatever comes to your mind, you can create this small self or independent standalone executable packages and then deploy probably on the same virtual machine. So that's the whole idea behind Docker or the containers. So the next thing is, what is important here? What was different, right, was the virtual machine approach compared to Docker. So this piece that you see here, this particular layer, which is defined as Docker engine, think of it as a single binary, which is installed on your VM. According to, again, Docker, it enables your applications which are containerized to run anywhere, consistently on any infrastructure, whether it's your local machine, whether it's your test environment, whether it's your production environment, and that also across different cloud providers or operating systems. One of the major problems that it's trying to solve is it works only on my laptop, or it works on my laptop problem, right? You may have heard about developers talking about the same thing. So the question is, okay, what are the different components that Docker engine is consisted of? It exposes a RESTful API over HTTP or using sockets, and we call it Docker API. And then there is a command line interface called Docker itself, Docker CLI. So that's what Docker engine brings, but also it brings a way where you can distribute your Docker images across different repositories. It can also help orchestrating your containers as well. This is the piece that we will be most interested in. We'll talk about it. You can actually provide some sort of disk space to your containers using volumes. If your containers are exposing some ports and you want to connect to those containers on those specific ports, Docker engine can handle all the networking around it. And then, of course, if you want to extend Docker capabilities, there is a build kit, and everything is, again, running and monitored using containerd daemon. And there is a lot of good plugin support as well. So it's a single installation of binary, nothing else more than that. Now, once we understand Docker engine, the next question is, what is the life cycle of a container, right, in terms of Docker? So pretty simple. I have an example of Nginx-based image. Maybe you have a React or Angular or just some static files. So you write your Docker file, which is just a simple text file with the specific name. You pull it from an existing base image, which can be any image available in the library of Docker, or which is called Docker Hub repository, or it can be just plain simple Linux image from Alpine Linux. You copy your code, whatever you have. And then in this case, I'm exposing 2 ports, port number 18443. So it's just a configuration about how I want my application, what I want my application to consist of, right? I want an Nginx image or Nginx process to be running. I'm copying my code, and then I want to expose particular ports. I run Docker build, which creates a Docker image. Now, Docker image is actually a layered system. You may have the base image, which is the Nginx, the lowest part of it. And every time you have commands like run, it's going to create new layer on top of it. And it's all to save resources while caching these layers if nothing changes. A lot of good stuff about that. Now, once you have an image, you can actually push it to a repository, whether it's a Docker Hub public repository, or you may have your own private repositories, wherever you want. And then when you run it using Docker run, that's the time when your image will go and become a container. It will start consuming CPU from your host machine, memory. You can optionally provide a volume as well. Think of it like a disk space. And if you are exposing any port, it's gonna open the ports for those communication as well, so that you can make requests to this particular container. In this case, I'm exposing HTTP and HTTPS ports so that I can talk to it over HTTP protocol. Now, anytime when a Docker container is running, it's gonna consume CPU, memory, and of course, volume. If you want to stop it, you can bring it to the stop state. It will not consume CPU memory. You will not be able to reach to it via the network ports. It may still be carrying volume bound with it, but it will be in the stop state. From there, you can bring it back to the running state, or you can create an image using Docker commit as well. This is an interesting concept here. At any point, you can remove it from the existence, whether using Docker RM or forcefully, if it's running. If it's stopped, then just do Docker RM, and then it will vanish, including your volume if it is not tied to your host operating system or some block storage. So those are some of the things that you may already know about Docker in terms of the life cycle. Just wanted to provide some overview here. Next things that you have around Docker engine, you have Docker CLI, which is what you use on the terminal to post commands like Docker build, Docker pull, Docker run, Docker images, Docker container ls, whatever you have. And you are always talking to a host, a Docker host, right? Now, this can be a daemon process, maybe running on your own machine. For example, I have Docker installed on my Mac, and it's running right now. I have, I think, the latest version right now, and that's controlling and containing a lot of stuff. It's a single binary, as I said, single process. Docker daemon is one thing that manages all the containers running on my machine and cares about all the images that have been generated from my Docker files. Optionally, you can use Docker daemon to send these images to some central Docker repositories. And one of them is, of course, Docker Hub. You can also have private repositories on your company's cloud providers, whatever it may be. The whole point here is this is the ecosystem you are playing with when you are dealing with Docker. When everything is so powerful like this, where you can create a lot of independent, isolated images and run them as containers, why don't we Dockerize everything, right? So that's one of the things that we here at Enoch are very passionate about. Everything that we have runs within Docker containers, as I said before. So what's the benefit? Again, going back to docker.com. So what Docker says, and we have understood as well, it actually provides an industry standard for containers, so that they could be portable anywhere, whether it's Linux, whether it's cloud providers, whether it's AWS or Azure or Google Cloud, whether it's Mac, Windows. Well, Windows took some time, but yeah, it's also there. If you go to this particular link, you can see majority of your frameworks that you deal with, the tools that you deal with, have a Docker Hub repository for it, whether it's Nginx, Alpine Linux, Redis, Mongo, you name it, and it's there. Postgre, all your databases. Whether it's Docker itself, and then a lot of operating systems available as well. Java, WordPress, RabbitMQ, Console, PHP if you want to run it in a Docker, Drupal, Neo4j, SonarQube, even Cassandra for that matter, Jenkins that we use, as I said before, in Dockerized environment, and a lot of good stuff. So you can go on, and these are all official libraries available from these providers onto Docker. So you can understand the standard that it's trying to create. Another good thing with the Docker, when you containerize your applications, is that You allow your containers to share your machine's operating system's kernel, but then you do not require an individual operating system per application, right? The approach that you may have been using in your VM-centric era. So definitely you are having now higher server efficiency. You can bin pack your server with as many as containers, as many as applications you can think of. On an average, somewhere around 5 to 10 times, you can increase the server efficiency by deploying many apps onto the single VM, definitely reducing server and licensing cost with it. Third point is about security. So Docker claims to be providing strongest default isolation capabilities in the industry. Definitely, because there is no one else as popular as Docker. So the security makes sense there. They have been working for a long time to avoid multiple containers sharing anything other than just a volume if it's required, or just some of the kernel libraries, the core kernel libraries. Rest of the libraries will be part of your own Docker image and then hence Docker container as well. There is still a security issue with the user ID isolation, but then you have to make sure that your orchestration framework is taking care of that. So going back to the state of Docker, of course, you can run it on Linux, Mac, Windows, any data center, whether it's on-prem or on the cloud, you can run Docker very easily. And that's one of the reasons, because of the support from everyone, Docker is so famous. Now, let's talk about some of the benefits that you may have using containers, right? When you run applications in containers. The first thing is, of course, the application isolation. In very general terms, think of, let's say you have 3 Java applications. One is using Java 6, one is using 7, one is using 8, and you may want to deploy onto the same VM. In this fashion, when you have containers, they can all run on the same VM because everyone will have their own version of Java internally to them, right? That's how you configure within your Docker images itself. So it provides a natural isolation among apps running on the same system or same VM. Because of that, you can provide some sort of multi-tenancy. Maybe a customer wants a specific version, or maybe you have a legacy application which is still running the old version of the library. And that can be true not just for the Java, but also for your Node.js applications, maybe your PHP application, maybe different versions of databases. You can definitely run them side by side with this isolation that you get from Docker. Definitely, you're going to be increasing your server utilization by a factor of 8 to 10 compared to the VM-centric approach, and you're going to be reducing the cost here as well, right? Another benefit that you get by using containers is very small startup time. That means within few milliseconds or 1 or 2 seconds, your apps can be ready to start serving requests. That means you can scale it very nicely and easily when you want to scale from, well, let's say 1 to 10 or any sort of configuration there as well. And then, of course, whole point is how can you make your application available 24/7, right? Even during the deployments, you do not want to take down your applications. Now, think of services like Uber or Netflix. I mean, have you ever seen them going down, posting a note to you saying, well, we have a downtime or upgrade is going on or a new release is going on or anything like that? No, you can't. They can't afford it. So these are some of the systems that helps making sure you have 24/7 availability. So these features or benefits on the end client side, right, on your production system. But what about developers? How it helps developers? So one thing that Docker has made very simple now is your developers, if they are using Docker, they can reproduce the same exact environment of the application on their laptops. And this environment can be just as same as your staging, your prod, in configuration at least, if not in data. They can debug very well because they can freeze the state of the containers and bring it to their laptops, and then they can start figuring out what went wrong, and they can check the logs. They can access the logs easily. They don't have to do SSH to the nodes. We'll discuss this particular piece in a few minutes. So a lot of features or a lot of capabilities, it's now giving back to the developers as well. So pretty easy. Think of running, let's say, 9 to 10 microservices on your machine because you are trying to test one specific flow that requires 8 to 10 independent microservices. You can easily do with Docker and some other utilities like Docker Compose. Another thing that has helped developers as well as operations folks in DevOps team is the configuration management. You can actually securely pass your secrets like your passwords or some other secrets. You can pass environment specific configuration to these containers, and you can externalize all of those things. You don't have to hard code these things anymore with your source code. So that's another good thing that you get with the containers. And then if all of these things are there, you can easily achieve some sort of automatic deployments, assuming you have very good rate of automated testing as well. And then you can do rapid deployments even to your production systems. You can think of, if you have heard about blue-green deployments or maybe rolling updates, you can achieve it because all of these containers, if they are orchestrated in a well-defined fashion. So these are some of the benefits that you have. If we know all these benefits and we understand it, the question is, what do I need to run a Docker container? So if you remember this diagram, the only piece that was supposed to be installed was just this Docker engine, right? It's very easy to install. You can just go to docker.com, go there, find out the download link, and then you can download it for your Mac, Windows, Linux. It's available in most of the repositories for these major operating systems. There are AMIs available on AWS, which are having Docker installed already into them. So a lot of support is already there. What you need is just a Docker engine, right? So if that's it, and then let's say you have a monolith REST API, which is installed or deployed on an EC2 instance. Maybe it's talking to a database behind the scene. For example, in this case, I have noted it as a relational database service from AWS. Maybe you have an Nginx front or a web server sitting in front of it. Maybe because you have an UI app there and it's proxying back an API request to this API monolith. So that's all is going on. And you eventually figured out that, you know what, your API, single instance of your monolith API cannot handle a lot of load, or maybe there are different components that should be independent than the rest of the stuff. Maybe you want to break it down, right? You may have heard about pattern called microservices pattern. Maybe, for example, in this case, let's say you actually break it down into two types of services. One is for, let's assume it's authentication piece. The other one is where you have a lot of business logic, which is talking to the database and something like this, right? Now, maybe your business service was the bottleneck before, so you replicated 3 times versus the authentication service. Maybe that was just twice. And then you can also containerize your Nginx application as well. So in this case, you have broken down your single monolith into multiple services, and then you can scale them independently as well. Now, Docker comes with a simple tool called Docker Compose, which will allow you to link these containers to each other so that they can talk to each other, although they are all containers. API or the first service can talk to the other service, and you can manage all those things. You can configure it in a YAML file, give it to Docker Compose. It will all work fine, no problems. But that's not always true, right? Every application will go down eventually. Every production system will go down eventually. It's how fast you can recover. And that's the hallmark of a DevOps automation system. So your application may go out of memory if someone is using them. They may return a non-zero exit status. In C++ or C cases, if you remember a segmentation fault, they can go in that state as well. Maybe the server is going down because your cloud provider is unreliable, or something happened to the cloud provider in that AZ or in that particular region as well. Maybe there are network outages on production systems. So things will go down, but you don't want a human to spend time to figure out these issues and then constantly restart containers and monitor them around the clock. You want all of these things to be automated. And that's the whole point. How do we do that? Because once we understood the containers, okay, fine, we broke them down, we deployed them independently, maybe on the same EC2 instance, but how do we still handle all these issues? So ultimately what we want apps to come back to life if they crash, right? We want them to come back to life. We want these applications that we deploy in the container fashion now to scale with the load. So let's say if there are more users hitting your systems or your APIs, you want to scale them, right? You want to increase number of replicas. If your applications are crashing, your developers actually would want to see where are the logs, right? Can they look at the crash reports, or can they look at all those things, even if those are running in productions? You want your applications to be backed up, whatever state they are, and there should be an ability to restore from an earlier point in time. Because, for example, if disaster occurs, you want a recovery from there as well, and you want that fast because maybe your clients are having very tight SLAs. You want your apps to be monitored in real time, and you want all of them automatically, right? That was very horrible animation there. So we want all of those things. But there's another thing that comes when you are dealing with containers. Because think about this scenario. Let's say you are using Docker Compose and you are manually configuring connections or linking these connectors one to another. That will still not be sufficient. For the UI app or the Nginx app, for example, here, you want to know what's the IP and the port of the backend service, while that layer may want to know about the IP and the port of another service in that layer, right? Or maybe database as well. So you need some sort of service discovery, an ability so that an app can find another app without too much of hard coding into the code itself, right? You want load balancing as well. For example, here, in this case, you had, 3 replicas of the same service running behind. You want some sort of load balancing so that you can distribute traffic equally among multiple containers, multiple replicas of that particular app. Then you also want to handle configuration. You want to externalize your secrets so that they are not embedded into the code and everyone has access to it. You want to keep it secure, but then pass to these containers at the runtime, maybe using environment variables or using proper concepts of secrets. You don't want to hard code these things into the source of the app, right? And then, of course, you want whether the container is live or it's ready to be serving the request, right? You want some sort of health check monitoring as well. And then you want, of course, high availability of your applications, all of the applications, wherever they are running. You want them to scale with the load. You want maybe to scale down as well when the load decreases because you want to save money. You want to auto restart them if something crashes. You want that for the containers as well as your virtual machines or nodes, if you can call them. And then when you go for the releases, as I said before, you don't want to bring your production system down even for a minute, forget about hours of being downtime. So there are new concepts like blue-green deployments or rolling update coming into picture now because they allow these particular kind of patterns allow you to have 0 downtime deployments. It's pretty cool stuff actually. And then I'm not sure if you are familiar with the concept or the principle called 12-factor app. Pretty good idea about how you should be coding your app in this era. And you will understand that using containers and an orchestration framework like Kubernetes, you can actually achieve most of them whenever it is dealing with the infrastructure from that part at least. So you can handle a lot of these good options provided by this particular principle. So you want all of them, right? Just having Docker will not help you. You need someone who can handle all these issues and provide nice abstractions with proper solutions for all of them. So that's where orchestration comes into picture. You need someone who can give all of these benefits to you, right? DCOS or Mesosphere was one of the first one to come up with this way back in 2013, probably the same time when Docker came with containers, or at least got popular at that point. I think it was first released in 2013. Now, originally, it was from the open source project from Mesosphere called Mesos and Marathon. And then they later on combined them for the enterprise version, called it DCOS. Then, of course, there is an interesting orchestration framework called Docker Swarm. It is actually natively inbuilt within your Docker daemon itself or your Docker engine itself. So if you go here, I don't have it available here because it's not configured, but Docker Swarm was Docker's idea of orchestration. And I think they had it for a long time in early 2017, probably January 2017. They released a beta version integrating Swarm with the Docker engine itself. So that was one. And then in 2014 came Kubernetes. There is a very good story actually around Kubernetes and Docker. So somewhere, as I said, in 2013, Docker released its V1, right? In 2014, Google approached Docker. Google is the original contributor to Kubernetes for your information. So Google approached to Docker to collaborate on this container orchestration framework that they have been running or kind of growing for many, many years internal to Google. At that time, the new startup Docker said no to Google. And Docker itself went on to create Docker Swarm. So Google said at that point, fine, we will give this Kubernetes project to CNCF, which is another open source foundation, Cloud Native Computing Foundation to be precise. They later renamed it to Kubernetes. It became gold standard of orchestration framework almost within 3 years of its existence. Many companies, many projects have started using it. And then there is a good support of it now. Last year, in November 2017, Docker realized their mistake. Then they started saying, you know what, we will support Kubernetes natively. And now I don't think there is a future for Docker Swarm anymore. And that's why, if you see here, it has a native support of Kubernetes. And Kubernetes is actually available for local deployment, as well as it can support natively within Docker as well. So that's pretty good open source collaboration now between Docker and Kubernetes. Same thing goes for DCOS as well. I think last year or sometime early this year, DCOS is also supporting Kubernetes for the orchestration natively, because they also understood from their clients and then all the popularity that Kubernetes is having over the last couple of years, especially. In case of Enoch, we have used all three of them. For some of the major clients, we have used DCOS. We started almost 4 years ago with Mesos Marathon, moved on to the enterprise DCOS. We have used Elastic Container Service from AWS as well for one of the clients. We have internally used Docker Swarm as well for almost a year before moving on to Kubernetes at the start of 2018. And that's what we have been playing with now. So pretty good, interesting stuff. So let's talk about Kubernetes. So it's an open source, production grade container orchestration framework, originally developed by Google internally, then donated to CNCF, which is Cloud Native Computing Foundation. It's pretty interesting foundation, actually. If you go and see some of the projects which have been graduated to their rating, Kubernetes and Prometheus is a couple of them. They have a lot of incubating projects as well. Most of them, or I should say almost all of them, are in the same container or orchestration or DevOps or SecOps world. They have some sandbox projects as well. Every project that goes into the graduate project takes pride on themselves. So Kubernetes is one of them. And of course, you can go and check out Kubernetes on kubernetes.io. They of course talk about a lot of stuff, including running on a planet scale. They claim that since it is Google is behind their initial days, so of course, where they used to run billions of containers a week, Kubernetes can scale without increasing your ops team. That's definitely one benefit that we have seen. And a lot of other stuff as well, including support for most of the cloud providers today that they have, or running on bare metal as well. If you go and check out their open source repo on github.com, you will see nearly 42,000 stars, a lot of commits and pull requests going on, a lot of changes. They are growing and have been growing very rapidly. As I said, it's actually all built upon 15 years of experience of running production workload at Google. There was a paper, originally it was called Borg. Maybe they changed it to Omega, and then when they gave it to CNCF, then renamed it to Kubernetes. They have been using it internally for a long, long time, at least the idea of containers, right? Google is an interesting company for utilizing your commodity grade machines for a long, long time. Remember MapReduce? Yep, this is probably from the same factory for containers, right? Using this. Going back to the support that Kubernetes has. So think of this. All the major cloud providers today have dedicated managed services, whether you are talking about Elastic Kubernetes service from AWS, whether you are talking from Azure Kubernetes service, whether you are talking about Google's Kubernetes engine, which is also supporting natively on the Kubernetes, or even if anyone is using IBM Cloud as well. And these are just the 4 that I have listed. You may find many other cloud providers also providing Kubernetes as a dedicated managed service. So pretty good stuff. When was the last time you saw all major cloud providers jumping onto a single framework, right? Maybe SQL database. And of course, you can run it on local or on cloud, one of those, or even bare metal. There is a different module in Kubernetes called Kube Spray, which will allow you to run Kubernetes on bare metal as well. And then, as I described almost in the last 1 year or so, other orchestration frameworks like Docker Swarm and DCOS, they have also started supporting Kubernetes natively. So definitely, it's the ultimate winner right now. Cool, a lot of intro so far. Let's talk about what's the architecture of Kubernetes, right? What are the components that you have in Kubernetes? So that's it. This is all the architecture of Kubernetes. So let's break it down one by one. So let's say you have your VPC or virtual private cloud set up maybe on AWS or on Azure, or let's say Google Cloud. One of them doesn't matter because Kubernetes support all three of them natively. So let's say you have a VPC, and then what do? You actually run 3 nodes there, right? Let's classify them. One is the master node, and let's say I have 2 worker nodes in that case, right? It's still the client server communication pattern or the master worker pattern that Kubernetes follows. So all of them are just running a Docker daemon, nothing more than that, right? All of them, whether it's master or the worker, they are all running Docker daemon. At this point, there is no differentiation between master and the worker. They are all same in this case. Then you start installing, or let's say running few containers. On master, you have, if you run this 5 containers, that's called a Kubernetes master. What are these? So it's a Kubernetes Kube API server. There is some scheduler going on. There's something called etcd with a database icon. So it looks like a database storage for this. Then there are a few controller manager, cloud controller manager. Don't worry, we'll go all of them one by one. So these are the 5 things that you run using Docker containers, and they are all provided by Kubernetes. So you don't have to worry about finding the source code or anything. They are provided as Docker images. On the worker nodes, you have to run 2 specific containers. One is called kubelet. The other one is kubeproxy. And then you have to run both of them on each of the worker node that you have. And that's it. Now, of course, you have to run them with proper configuration, mostly all requiring where is your Kube API server. So you can easily see here with this diagram, Kube API server is the most important part here, right? It's actually the central communication point with everything in your cluster. Everyone is either talking to Kube API server, or Kube API server can only the one which can talk to the other components, right? So what is a Kube API server in this case? So it's a component that stays with the master or resides on the master, and it exposes a RESTful API, a secure RESTful API that it exposes. You can think of it as a process that can accept the REST request, validates what you are sending to it. Of course, it will make sure that you have proper access to it. RBAC, a role-based access control that we'll go through in the 3rd session from now. And then, of course, it validates whatever payload you are sending in the RESTful API request, and then execute the business logic or whatever is meant to be. So Kube API server is the most powerful component there. The next important thing is etcd cluster. And I said cluster, that means there are definitely more than one, or it's deployed in a clustered fashion. So what is etcd? So it's a very simple but very highly available key value data store. So you can think of it as a database where Kubernetes stores every configuration that is there on the Kubernetes. Where are the nodes? Where are the application deployed? What are the names of the services? What ports these applications are exposing themselves? Where are other masters? Because you can also have or multiple masters as well for high availability, right? All those kind of stuff. So every configuration is stored in this etcd cluster. That means you have to make sure that this is highly available and backed up as well frequently, because if you lose this, you will be losing your cluster almost. You can of course get it back if you back it frequently. So that's your etcd cluster. Think of it like a database cluster. The 3rd thing here running on the master is Kube scheduler. So by the name, it means something related to scheduling, right? Yeah. So let's say when you ask Kube API server to deploy your particular application, Kube API server needs to know, out of all the available nodes, where should I go and deploy it? That's when Kube API server will take help of the scheduler, and scheduler has all these things into its account. It will take, okay, what are the resources that this application needs, and what is available outside on those nodes, right? On this particular worker nodes. Are there any hardware constraints saying, you know what, run this application only on the bare metal? Are there any software or policy constraints? Something like, oh, run this application only in this particular availability zone, or maybe only on on-demand instances, or maybe only on spot instances, right? Those kind of things. That includes affinity and anti-affinity as well. Whether you have to run this container where the volume is available, and a lot of these things. So that's the headache that scheduler simplifies it for Kube API server. So that's the job of scheduler. Then you have few controller manager. One of them is Kube controller manager. So it is the component, again, running only on the master, that has all these daemons to do specific jobs, different processes internally. It has something called node controller, which figures out how many nodes are running and what to do when a node goes down. For example, if a node goes down, all the workload running on that particular node should be transferred to the other worker nodes, right? And it tells Kubernetes, or node controller then tells it to the API server to do that. There is also a replication controller, which makes sure that when you said, you know what, for this particular RESTful API, I need 5 containers. Yeah, it keeps that record in it. That's the replication and controller. Let's say your application is exposing some ports so that your users can reach out to those applications. You need to figure out where are those containers or applications running within your cluster. Maybe one of them is running on this, the other is running on this. So you need someone who can bind the IP and the port and keep a record of it, right? So that is the responsibility of the endpoint controller. Then, of course, you have to deal with a lot of security things about who is accessing what, whether it's allowed or not, whether there are credentials required. Kube API server works solely with your certificates and verifies your certificate with what is stored and a lot of security related stuff. So that's the job of another controller that you have there running on master. The last component on the master in this diagram is actually the cloud controller manager. Now, initially when Kubernetes came, this responsibility was also inbuilt within the Kube controller manager, but then later down the line, they realized, you know what, this is doing a lot of cloud providers specific things like, you know what, I need to find out routing table configuration. Well, that's a different thing for AWS versus Azure versus Google Cloud. So they put it here in the route controller. Someone need to find out load balancer specification, right? AWS handles it differently using ELBs. Azure will be handling it differently. Google Cloud will be handling it differently. So that code resides in the controller manager. Then let's say your application needs some hard disk, technical word, volume. So in case of AWS, you need to provision EBS volumes, right? Elastic block storage, or EFS to be precise. There will be something else, some other ways to provision on Azure and separate on Google. So that's also the responsibility of this particular manager that you have, CCM. So that's the whole point of CCM in this case. Now going to the node side, you have two things, right? Two containers from the Kubernetes configuration running there. One of them is kubelet. It's a simple agent that runs on each node in the cluster, and then it gets a configuration about what application to be running, and then it constantly checks whether that application is running or not. Technically, it checks for the container within the pod, whether it's running or not. If it has died, it will make sure that it comes back up. And of course, it also communicates with etcd via API server only. None of the Kubernetes components on the nodes can talk to anyone else except API server. One of the last things that you need on the node side is the service discovery, right? You want to identify where are your applications running on that particular node. And that's where kubeproxy comes into picture. It acts as a network proxy and kind of a load balancer for all the apps on a single worker node. It takes care of all the forwarding related to TCP and UDP packets. And that's the job of kubeproxy. So these are some of the major components that you have in Kubernetes ecosystem, at least some of the ones that you require. There'll be some other components as well. Maybe you want to have a centralized logging. So you may install FlowND or some other sort of logging drivers. Maybe you want specific monitoring as well. You can install metric servers and a lot of other stuff as well. But at least you need this kind of components or modules at least available on your Kubernetes cluster. So it was all good and fine, but everything was running within the cluster, right? And if it was a VPC, then you need some way so that you can tell the API server to run a particular workload or deploy a particular application from outside the cluster. And that's where kubectl comes into picture. In short, it's just a command line interface that you can execute from your terminal. And you can connect it to the API server, because remember, this is exposing a REST API. It's very powerful REST API. If you have control to API server, you can actually do anything on your Kubernetes cluster. And you can connect to API server from kubectl. It's just a command line interface, but very powerful one. You can pretty much do whatever you want. You want to create, you want to delete, you want to update, you want to describe, you want to execute any Kubernetes object, and you can control it if you have proper access to Kube API server via kubectl. You don't even need SSH access to these nodes if this particular connection is configured properly. And in our case, for example, here, we deal with and we connect to all of these parts or applications running even in different nodes on our very large cluster, but we never need to do SSH access to these nodes. We can directly use kubectl to directly go into the container itself. So these are some of the components that you will deal with while working with Kubernetes. So let's see how it works. Let's say you want to deploy an app. So ultimately what you need is actually, you need to tell Kubernetes, or kubectl to be precise, you give a simple YAML configuration, and then you will post it using kubectl to API server. Let's say you want to deploy a simple, an Nginx app, right? Which is just having static files for your static website. So you tell kubectl to post it to the Kube API server, assuming you have all proper access. So what Kube API server will say, well, okay, let me figure out where I can deploy it. It will take the help of scheduler and then figures out a node where it should be deploying the pod. Now you will see, okay, what is a pod? Weren't we talking about containers? So in case of Kubernetes, or in Kubernetes world, the smallest and the simplest unit is not container. It's actually a pod. And within one pod, you can deploy multiple containers. We'll talk about it in a few seconds. So in case of pod, think of it as a running process inside a cluster. Kubelet is constantly looking at it and making sure all the containers within that pod are running, up and running. And of course, it can contain one or multiple containers. And let's say you want to scale it up, right? You are not happy with one container. You may want to scale it to 4 containers or 4 pods in this case. I'm interchangeably using pods versus containers in this case because there is 1 container per pod. Things may change, but at least for this use case, it's fine. So in this case, now I have 4 pods running of the same application, but they are of course running on different worker nodes. But what's there if you cannot access these pods, right, from outside? Maybe these are Nginx pods, an Nginx application is running in, or all of them. So you want to access from outside, right? That's where you can expose the ports, and then kubeproxy will come into picture and set up your networking with that, right? So far, the kubeproxies only will take care or will be available only within the cluster. But maybe you want to expose your awesome static side to the world outside. And that's where you can have one more abstraction coming from Kubernetes that can talk to the cloud load balancer available as well. So maybe on AWS, if you have set up your VPC on AWS, you may just configure an ELB for that. And Kubernetes can do that for you. You don't have to code and set up Elastic Load Balancer for yourself. You can just configure with one single word, and then it will set it up for you. You will have the DNS available for it. You can go and hit it. Depending on the security groups, you will be able to reach one of these pods because kubeproxy will do the load balancing for you. Load balancer, on the other hand, will do the load balancing between the nodes because that's what it understands, right? ELB has no clue of containers or pods or anything. It only knows nodes, the EC2 nodes, while the kubeproxy, on the other hand, knows how to load balance between multiple pods. So that's simple logic behind networking. Then you say, okay, I have another app, maybe this time a Node.js app, same story, nothing changes. Kubelet will take care of the container inside it, making sure it never goes down. If it goes down, it will bring it up. Kubeproxy will take care of the networking part of it, right? Then you will be like, yo, all good. These are all so far have been stateless apps, right? They are not storing anything. Request comes, processes, response gets out, nothing is stored, no state. That's why it's stateless. Next thing comes, let's say, what if you need to store and your pod need a hard disk, right? A volume to be precise. And that's where you can actually have a volume attached to a pod as well. Now, when you are on the cloud, what you have are something called storage blocks. on AWS, you can use Elastic Block Storage, you can use Elastic File System, whatever, one of those two, of course. You can say, you know what, Kubernetes, for this application, I need 2 GB of hard disk. Give it to me, attach it to my pod wherever it's running, and I'm gonna mount it within a certain path within the container. Easy. You do it with a few lines of configuration in your YAML file for your application, and Kubernetes will make sure that it will talk to the cloud provider using the CCM, and then will provision 2 GB of Elastic Block Storage in this case, if it's on AWS, will attach it with this node, and then your pod will be able to access it. Simple and easy. Think of, let's say, your Jenkins. This is how we deployed Jenkins. Jenkins stores everything on the disk, right? There is no database. So it stores everything in the configuration files, in XML files, and they reside on the disk. So it needs a volume. Kubernetes can do that. You need, let's say, WordPress to be deployed. That's how we have deployed our all client and our own site. So in that case, also you need file system to be available to you. You can ask for it. And that's the beauty with the pod. And of course, asking for the volumes from the block storage, or CCM will manage all of that stuff. So all good. You can run stateless, you can run stateful as well. Cool. Let's talk about a pod running multiple containers and also having volume, because this is one of the most interesting things that differentiate Docker Swarm and everything else versus Kubernetes. So think of a scenario, let's say in this case, now I'm thinking, you know what? I don't want to use a separate MySQL database for my WordPress site. I just want to run both WordPress and MySQL within the same pod. Not recommended, but you can do it. You can run both the containers. So think of A being the WordPress container, B being the MySQL container, and they are sharing a volume, meaning they are sharing a hard disk. Fine. Of course, you have to make sure they are talking to different directories in that volume. That's all in good. The good thing about this particular pattern, which is provided by Kubernetes, is, let's say if A wants to access B, and since both of them are running in the same pod, let's say B is MySQL exposing itself on port 3306, container A, let's say in this case WordPress, reach out to MySQL just using localhost, because all the containers within a pod are sharing volume as well as the network interface. So container A can just say, okay, my database is running on localhost 3306. And yeah, it will be available there. So that's a pretty powerful concept. That's the most important feature, in my opinion, that allow any VM-centric operation that you have been running so far, you can migrate it on first day using just the simple lift and shift operations to a brand new Kubernetes cluster without disrupting anything. Because from day one, if you are coming from a monolithic world, you may not have all the things in the containerized fashion, right? As long as you can create a Docker image, this particular pattern will help you at least starting a process or a migration and launching it onto a Kubernetes cluster. Very powerful concept here. The next thing is, what if you want multiple pods for the same app, but with dedicated volumes per pod? This is the highest, or let's say the pinnacle of configuration that you would need. Think of some of the clustered applications or clustered services like your databases, right? In a clustered fashion, not just a standalone machine or a standalone service. Think of Kafka. Let's say you are running multiple brokers, right? Maybe you have HDFS or Hadoop running as well. And they, in this specific type of clustered applications, every service needs its own dedicated storage, right? And that's very highly complicated configuration. But with Kubernetes, you can do that. This is how actually here at Enoch, we run Kafka with multiple brokers in this configuration. We give them dedicated volumes because this application, whatever the service is, let's say Kafka in this case, running with Zookeeper, can have its own volumes. And these volumes are tied to a specific pod. There is a specific type of object for this particular load called stateful set. In one of the later sessions, we will understand this exact piece as well, because we want to understand how you can run these clustered applications as well, like databases, maybe a Cassandra ring that you want to run alongside, of course, your Kafka clusters or anything else. Very complicated, but very easily done on Kubernetes using this concept. So that's pretty much it here. Now, on the CLI side, because your kubectl can talk to API server, There have been a lot of other tools as well in this Kubernetes ecosystem, mostly on the CLI side, that will piggyback on kubectl to do a lot of cool stuff. There is a repository manager or something called Helm that's also piggybacking on kubectl. It simplifies writing complicated YAML file for the Kubernetes configuration. Instead, think of it like npm, where you can just do npm install blah, 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 and then you don't have to worry about, okay, how many things you have to bring down from the repository and install it and send it to API server. Helm will do it for you. There is another version of Jenkins called Jenkins X, JX to be precise. We started using it initially. We didn't like it, some of the issues with the stability of it. We went back to the original Jenkins, but still we are running it in the Kubernetes cluster. Later down the line, we'll talk about it, but that's the whole point. There are many other CLIs which are piggybacking on kubectl to talk to the Kubernetes cluster via this particular bridge. I think we are already at the time, and that's where I think I'm done with this particular example, talking about how Kubernetes orchestrate your containers. And it's pretty easy. You will see in the next 7 sessions how you can set up Kubernetes, whether on your local machine or on AWS. In a highly available fashion on AWS with multiple masters and multiple AZs, multiple nodes, of course, more than 1 node per AZ, making sure your cluster never goes down, right? We will be setting it up with a tool called KOps, and that's a very powerful way of setting up Kubernetes, especially on AWS. Later down the line, as I said before, we'll talk about security, how to run stateless workload, stateful workload, load balancing, disaster recovery, a lot of cool stuff on the line. So that's it for today. We'll again meet next Thursday and then understand how to set up Kubernetes on your local machine, on your Mac, Linux, Windows. You already got the hint. Kubernetes is actually already available. You just have to go into your Docker daemon and just go here and say enable Kubernetes. Pretty easy, but the complex part is how to deploy it within 30 minutes in a highly available fashion on AWS cluster. That's the major point that we'll understand next week. So thanks for joining us today.